So, CLWrap, nonsense-free control of your GPU. Why bother, right? What's the point? CPUs are great. So who here has actually written, say, I'm going to set the bar relatively low and say a shader, right? So no fixed pipeline stuff, that's not allowed, right? Or a like compute kernel or anything like that. Okay, so that's a reasonable proportion. Okay, so CPUs are really, really complicated these days. We've had a lot of stuff mentioned earlier in the conference about this. There's a huge amount of technology in them that is, it's really great for papering over the cracks of your rubbish code, but it's not necessarily, it's not going to be power efficient, it's not cost efficient if what you're doing is very simple, sometimes. So yeah, serial workloads was always the primary goal of our thinking x86. It's always been straight line speed, and then the sort of parallelism stuff has been tacked on the side. You go, oh, let's have some vector registers, let's put multiple cores on a chip and do good interconnects and stuff, but it's never been the primary goal of them, right? So GPUs, they're built from the ground up to do loads and loads of things in parallel, so they can have the sort of the economies of not bothering with all the niceties that is necessary to squeeze out every last bit of straight line speed and focus on the parallel. The really big thing is computer games. We can get amazing hardware for very low prices because there's an enormous market. So the production costs are way lower than they are for comparable sort of specialized vector processors. And everybody already has one, or two, or three, right? Every single person here, there's a GPU of some power in your laptop. Quite often, if you look up the theoretical peak, you'd be surprised that sometimes your GPU, even in your little laptop, is higher than the CPU by quite a bit. So it seems a waste. Like sometimes it's busy rendering pretty pictures on your screen, doing animations, but quite a lot of the time it's not really doing much. And I think there's an opportunity there. So that's why. So the options that people have for this stuff. CUDA. Anyone use CUDA? Right. Okay, so CUDA is NVIDIA's proprietary solution to this problem. It only runs on their hardware. And it's actually pretty good. I mean, it's a nightmare. It's horrible, but then this domain is all a nightmare and horrible, so that just goes as standard. So that's been very popular. It's probably the dominant player in general purpose computing. So when people build big supercomputers, perhaps not at the very highest end, but although sometimes, people put in a bunch of GPU nodes. That's the thing that people do. And it's always, pretty much always, NVIDIA cards. And people pretty much always use CUDA to program them. Kronos, OpenCL, and I just realized there's a typo, that should be KH, I think. That is an open standard that is put forward in collaboration with AMD and Intel and a huge bunch of other partners. I'm not sure if NVIDIA, I think they probably are a formal partner as well. So this is the open thing. The idea is that it's not fixed to just the one hardware provider. Oops. Then people just do compute shaders of various types with the various different systems that there are on different operating systems, direct compute, that sort of thing. Or the old school way, when GPUs were first getting to be really powerful and none of this stuff really existed, is you just use normal shaders and then do something like read the frame buffer back into main memory to get your result, things like that. So that's kind of the options that have been available to people. OpenCL, it's an open standard. And it's not really just about GPUs. It's about any system where you don't just have one homogeneous computing system. So you might have, the classic thing is a CPU host and a GPU device. But it doesn't have to be like that. It could be an FPGA. There are FPGAs that have OpenCL implementations for it. It could be a CPU host and a bunch of other CPUs as a together forming a device. All sorts of possible configurations and all sorts of weird hardware that you can use it with. I'm going to focus on GPUs here because that's kind of the most common use case, but you should have in the back of your mind that everything I'm talking about here could work for some strange coprocessor thing that you have, or anything really. Also, an aside, you can directly target OpenCL to your CPU. You can be your own host and target. And there's some interesting experiments that people have done and found that OpenCL can sometimes be extremely performant compared to just the handwritten code that you would normally do. Because it's designed from the ground up to be parallel, not necessarily that there's anything particularly clever it's doing, it's just forcing you to do things in a massively parallelizable way. So yeah, that covers that. So it's not really as popular as CUDA, at least in my experience. I mean, a lot of the big players who use this stuff don't necessarily talk that much about what they use. But the model of how it's sort of all described, because it's so abstract, because it's supposed to work on anything, is actually quite confusing, and it's always presented in a confusing manner. The other thing is the C API, which a lot of scientists in particular still use, as opposed to this, would like to use, as opposed to the C++ API. It's horrible. It's really not nice at all. So I'm just going to go over briefly covering how the basics of OpenCL work. So there is the idea of a platform. So on this machine, I have the Apple OpenCL platform. And every single one of the Apple computers here will have that already there. On every other system, it's much less pleasant, and people have to install drivers and things like that. It's a pain. And not all of the default drivers package OpenCL with them. But the idea is that you have one platform, and that represents one vendor's implementation of OpenCL that can target a bunch of different things. So if I had the Intel OpenCL on here, it would support both my CPU and my GPU as targets. So then there's the concept of a device, one GPU, that's a device. The context. This is horrible oversimplification, but from a lot of perspectives, you can just go, the context is a group of devices. It manages a lot of the state, and it does a lot of magic, but really, you group a bunch of devices together to form a context. The kernel, so that's like a main, effectively. It's an entry point. You write a little bit of code, you compile it into a kernel, and that's like a little, you can jump to that, execute the code on the GPU, and get your results. And that is compiled separately for every pair of device and context. So this is also compiled at runtime, normally. At least there's an intermediate language that's becoming more popular. But really, in order to have really good performance on the very wide variety of devices that we have available these days, having runtime compilation is really the only option, because if we took all the laptops in this room, every single one, you know, there'll be a few duplicates, but an awful lot of them will have subtly different versions of things. And they're just not compatible across. Command queue. So OpenCL manages all of your scheduling for things to run on the GPU. So it has a queue per device. Again, oversimplifying a bit, but there's a queue per device, and you can effectively drop a kernel in and say, please execute this on that device. And you could queue a whole bunch of things up. And then there's buffers and images. That's your data. That's the data that's accessible from the kernel. It doesn't actually have to be on the device. And in general, where the storage is and where the device is not actually specified in OpenCL. And you can explicitly say, I want my data to stay on the CPU in the main memory and be accessed through direct memory access from the GPU, or you can say explicitly, please copy it, and there's a few other options. So, the C API, if we're going to work from D, we're probably going to want to target the C API because it's going to be so much easier to bind. And it's sort of the fundamental, it's the fundamental thing for OpenCL. The C++ API, it's not that bad, but it's kind of a layer on top, a bit like what we would do in D. So let's try and report the names of the GPUs that we've got on a system using C. Actually, before I ask this, has anyone used OpenCL ever? That's actually a reasonable number of hands. Who's used OpenCL using the C API? Who's used it from the C++ API? Who's used it from something else? Is there? There's no hands there. Okay. That narrows my competition for this talk then, because you don't know about all the other nice implementations. Okay. Oh, clicker's not working. So we'll assume a huge amount and say that we've already worked out what platform we've got and we've got an ID for it. So let's work out how many. So we're going to work out how many GPUs we have. You call this function CL get device IDs with a bunch of a 0 and a null and a pointer to a return value. And that might fail for some reason. Then you'd want to allocate some memory for a list of devices. And then you call the same function again with a different set of arguments. So you go, instead of saying I want 0 and passing a null pointer for where you want it to put the result, you say, you give it the number that you asked for before, and a pointer to somewhere to store the memory, and then null for the last argument. And then we want to find out what they're called. So that's what you do. It's horrible. Now imagine yourself as like, okay, we all look at that and we go, yeah, it's a nightmare, but I've dealt with worse, right? But that's not great for industry traction, and it's also not great for particularly my experiences with academics who see that and then they see CUDA and they go, no. Ew. So let's try again in D. Now that doesn't look much. That doesn't look much better to me. Actually, it's quite a lot better hidden behind the scenes. So please don't take this as this is what it's all going to be like. It does get better. So in here, previously, I'm not going to go back, but any of these calls to these like get device IDs or get device info, you have lots of different types of handles for the context, the queues, the devices. So in C, you can just pass the wrong ones to the wrong arguments because there's no actual real typing there. It's just different words you write. It doesn't mean anything. So what I've worked on is making an exact copy of the OpenCL C API with as strict typing as I could possibly get without having to change the API significantly. And that's the base layer of what I've been working on. So, and that's actually done, and is that should be completely production ready now. So it means that you can use the C API, but you'll have a few less completely insane crashes. So that's always good. So let's do it slightly nicer. So that previous one, you noticed, was just a little snippet just to read the names and print them out. So in D, we're going to do a full program. We're going to read command line arguments. Yeah, please provide a platform name. Auto platform, get chosen platform with a name of what platform you want. Now, that still sucks, but hey, what can you do? People's hardware is going to be different. People's devices are going to be different. There is no such thing, really, as a sensible default. Not generally speaking. We could probably do something, but mostly you have to specify what you want. Devices, platform.getDevices, and I only want the GPUs. Map, getInfo, device name. Now, that hides some of the most terrifying code I have ever written. Because when you call, say, device getInfo with a different enum value, saying, I want the device name, or I want what's the maximum size of local memory I can have, or whatever, it does different types for every single one. Like there's like a list of, I think, in the end, you have like 18 or 20 different types that it can put into the void pointer that you've given it. So I have to wrap that in a sane API, which I did, and that was a huge amount of the work I've done. And now, anyone who's used the C++ API is familiar with this sort of idea that you can call getInfo with the enum value, and it gives you something that's of the correct type and you can use immediately. Joiner, write line, done. So that's a little bit better. I think everyone would agree that they'd prefer to write that than the previous one. Now, of course, yeah, there's some memory allocations hiding in there. But, I mean, come on. You're querying the names. I think you can afford a few allocations. So let's see what we got. So I'm going to go through and talk a little bit about how OpenCL works well, not really behind the scenes. You have to know in order to explain some of the higher level concepts I've been working on. So this is a very, very stripped back view of how you might look at a GPU from the perspective of OpenCL. Now, anyone who actually knows about GPUs knows that there's a huge amount of clever stuff going on. But fundamentally, this is the structure. So you have a device, the whole thing. You have work groups. And that's a bit, I think of them as analogous to a core, actually. Like if I was working on a CPU, I think of a work group like a single core. Now, there are ways that analogy breaks down, but I think it's easier to think about it that way. And then inside each work group, you have work items. And you think about that like one SIMD lane. So that's so say you had, using the SSE extensions on Intel, you might have a vector of 8 floats. Well, that would be AVX. And each one of those we have as a separate work item here. Now, there are lots of ways you can make it more complicated, but that's the basic concept for simple things. And each work group has its own little local memory that's pretty fast to access. So each item can store things in the local memory, and each item can read from the local memory. Everything in the work group operates effectively synchronously, but when you write your code, it looks like it doesn't. But behind the scenes, everybody moves in lockstep, including if you go if-else. And so imagine one work item goes, if you are an odd-numbered work item, do this. If you're an even-numbered work item, do this totally separate thing. The way it works in an awful lot of implementations is every single one of the work items does both branches, and then the hardware, in collaboration with the driver, is responsible for making sure that it erases the effects of having done the wrong one. Which is why it's actually easier to think about it like SIMD registers, like separate SIMD lanes, because you don't really have independent execution. And then you have global memory sitting outside. So that's where you can send your, that's where you've actually got some proper space. That's your main GPU memory, which these days is quite easily 4 gig, 8 gig. And that's obviously slower to access, and you have a lot less, I think the way to talk about this is that there's no, although on modern GPUs there are starting to be proper caching, the way that OpenCL works is that you hand manage your cache, which is that local memory. So if you want to access something repeatedly, you don't, if you think in your traditional CPU programming, if you go, oh, I've read it recently, so if I read it again, you know, if you give the right offering to the cache gods, it'll still be there. On the GPU, it's just ignored you. It read it from memory, and then once it's gone, it's gone. It's not waiting somewhere closer to you just because you read it more recently. Again, caveat, some more modern things, yes, it is actually waiting there. So what you would do is you'd read it into local memory and access it from there, and then when you were done with it, you'd remove it. So you have to hand manage your caches. So then I'm going to talk about the basic way that you express your parallelism. Now this is when it gets a bit confusing, and it took me perhaps an unreasonably long amount of time to understand what was going on here. So I don't know, maybe the font's a bit small, maybe I should have done less squares, but you have, every work item has the concept of a global ID and a local ID. So the global ID, if we go back to here, is your ID across the whole device. Again, assuming everything's simple, across the whole device. And your local ID is your ID within your work group. And each of those can be one-dimensional, two-dimensional, or three-dimensional. This example is a two-dimensional one, just because, well, I would do 3D, but that would be a bit difficult on the slides. So you can see here that it's just in green, the global ID expands is just what you'd expect from a Cartesian grid. And then the blue ones are repeated on every little subgrid. And that's the way it works. Note, it's evenly divided. So the local group sizes evenly divide the global size. And this is the source of a huge amount of pain. More recent OpenCL versions, it's a bit less painful, but still not necessarily perfect. OpenCL C. So that's the language that you write your device code. I'm actually going to skip past the fact that there is OpenCL C++. I'm not going to talk about that here. That's great, but it's actually only supported in much more recent versions of OpenCL. So there is OpenCL C++. That's all I'll say. So it's a restricted C. You've got some extra built-ins, funny type qualifiers. You can specify, take a pointer and say, that's in global memory or that's in local memory, for example. And it's got built-ins for all of your cosines, sines, all your math. And it's got really good vectors as well. Compiled at runtime for the exact target hardware that you're running on. Again, this is not necessarily quite as true, or at least it's more complicated now because people are compiling to SPIR, which is the intermediate representation. So the intermediate representation is agnostic to what devices you're on, and then that's compiled at runtime in order to run on your given device. So yep, you can tag pointers, global or local, to specify which memory they point to. The memory model is actually a bit worse than that, but that's the basics. No pointers to pointers. Everything is flat. Now, again, as always, it's a little bit more complicated than that, and if you use more modern versions, you can do some interactions. But the fundamental way of doing most things is everything is flat. You have an n-dimensional array, you've just got one pointer, and that's it. So a function annotated with kernel as an entry point, think like a main, as I said earlier. So let's go through and talk about some really boring kernels to illustrate some of the points I was making there. So can everyone see this? It might be a bit small, but is that okay? Good. So here you can see you've got a kernel. It takes a global float pointer with your input array and another float. It gets its global ID for dimension 0. It's assuming that it's just working in a one-dimensional space. And it just, the ith input, which is the one that it's supposed to be looking at, is equal to the exponential of the ith input times b. And that gets executed That gets executed once per global ID, and if you, assuming you're doing something normal, that maps to one element of your array. So you'd evaluate that expression on every element of an array. So please do stop me if it's confusing at any point. Yep? Yeah.
Conceptually here, if input has more data items than you have global IDs, is this just going to modify a fraction of the data?
Your input can have more than your global IDs. Your input can have less than your global IDs.
But in this case, is just the first global ID worth of data modified and everything else left alone?
Sorry, you have to speak up. I can't.
In this case, is the first global ID number worth of data, input data points modified and everything else left alone?
So this is evaluate. You imagine this function is done. This is a work item. So that gets run. That grid that we saw before. This gets run on every single one. Actually, this is a 2D grid, but if you imagine it's just a big long row, you'd have one for every single one of these. So assuming that you gave a buffer that was the same size as the number of global IDs you wanted, then you would be looking one for one, and each work item only touches its element.
Okay.
Yep. Well, got to go through. Another boring kernel. So this is, let's do a 2D one that writes to an output. Pretty much the same idea, except that you have to get your global ID on the first dimension, multiply it by the global size of the second dimension, and add the global ID on the second dimension in order to work out where you're supposed to be indexing into some big flat array. And then I've just done the inverse. So that's pretty simple. But you can do that. This is sort of illustrating how general the system is and how difficult it can be to find any universal abstractions. So here, actually each one reads from a random location in the array and writes to a specified one, because obviously otherwise that would be there'd be a data race. Oh yeah, by the way, there's no protection against, you can't assume any protection against data races unless you manually synchronize things, as far as talking to global or local memory is concerned. So what I'm trying to illustrate here is that the work items don't in any way have to map to the memory. It's totally up to the programmer to decide that they spawn. It's a bit like sharding if you are used to sort of doing your web scale stuff. You could have one server mapped perfectly to every single data item that needs to be processed, but you can actually chunk it up any way that you want.
You said lockstep, right? They always get the earlier state's value?
They work in lockstep, yes, but you can't rely on them working in lockstep. Because, so for example, if you had you can specify more work items in a work group. So the hardware and the runtime together will have a limit on how many work items you can put in a work group. But that limit doesn't necessarily correspond to how many actual slots it's got free ready to put things through. So it may be that it runs the first half of them first, then the second half of them second. So if I wrote back to the same memory there, even though conceptually speaking you can think of them going in lockstep, it's quite easy to end up with a data race that way. So the CLWrap architecture, this is the library I've been working on. There's a level 1, which I talked about before. That's take the OpenCL API, strict typing, reduce a whole class of bugs, and much more importantly, make it so that you can use all of D's metaprogramming on these things. You can tell at compile time if you've got some higher level function that you've been passed some specific OpenCL type. You're not just stuck with a void pointer effectively. So then there's the take the strictly typed layer, do the more D-appropriate API. That was what I showed you before for printing out the names, which was a lot nicer than the C-style way of doing it. And then there's the level 3, which is the go to town, do some higher level abstractions, make some assumptions. Now, yeah, some people who were here last year might recognize this slide because I stole it from last year's presentation. So let's do it live. Let's, yeah, dangerous, right? So, well, first things I just wanted to show you guys this before I do that, because it's just to show you the sort of API we're working with here. Okay? Yeah. So that's fun. So you can see there's good reason why you might want to have some sort of wrapper around this. Luckily, that's not one that you have to call twice in a row to get some data back first that to then be able to work out what to create in order to call it again. It's nice like that. Okay, so where am I? Nope, that's the wrong one. So it's going to be slightly difficult to see, but I just wanted to do it live to actually show you your way through it. You can create a kernel. This is actually just as a global variable. You define a kernel, give it a name, define parameters for it, give them names. Then write your code, again, as a string. So in this case, it's taking the exponential of the cosine because whatever, something off the top of my head. And you notice there's a few conveniences here, like no matter how many dimensions this is called in, OpenCL only really goes up to 3. But if it's 1, 2, or 3 glin ID maps, it is just worked out automatically for you as being that business of multiplying by the strides that's necessary to work out your linear index. So that's not so bad. You can write your kernels like that. Then get a platform. We get devices. So it's a bit difficult with the text size this big because the lines are a bit long, maybe a little bit smaller, but I don't want to go so small people can't read it. Nah, it's not that much better. Never mind. So, and then you create a context, you create a queue, then you create a kernel. You create a program out of the kernel, you build the program, and then you extract the compiled kernel from that program. Now, this may look a little verbose to just get started using a GPU. You've got to bear in mind that every single one of these in the C API is a call in order to work out how much memory you need to allocate in order to make the call again. And so the whole thing expands out, and when you buy a book on OpenCL and they do the C API, you'll see the like hello world example will be many pages long, often, because of that. So let's create program, and then let's just, very simple, create an array of things from 0 to 89. Make it into a buffer. Say we want to copy it to the device. Set the arguments to the kernel. Say, I want to make, you bind the arguments to the kernel. You say, I want to this kernel called with that buffer and 1.4. Then I enqueue it on the queue that I created earlier, and I'm enqueuing it as a 10 by 9 global thing. That's very small, obviously. You would never do that on a GPU. It's a complete waste of time. And then, so then at that point, it's been enqueued and is running. Unless there was already, unless the device is busy or whatever, but you can think of it as running then. Then you create, I'm just going to create an output array and read. And I'm going to do something nice. I'm going to delete that because that's the default now. Because it's pretty rare that you don't want to block the non-blocking cases of the API are much more difficult to use, much more convoluted. They're often necessary, but I really didn't think that they should be the default. Because quite often in an application, you want to, sort of the best case situation is when you can give a bunch of data to the GPU, it then whirs away and does loads and loads and loads and loads of work on it, and then tells you what the answer is. So worrying about you really want to not have to worry about the latency across the PCI Express bus to get back from the GPU or however your device is attached. Sometimes you do have to worry about it, but the not-blocking API is so spectacularly bug-prone. It's really, really difficult to get right. I mean, maybe really, people who are used to doing asynchronous programming by hand, maybe it's fine for you guys. For me, I use it when I absolutely have to. Oh, also, worth mentioning at this point, queues are not necessarily in order. You can queue a bunch of kernels to run, and you can say when you create the queue, I'm perfectly happy for this to run out of order. Which then means you have to take care of making sure that everything's finished. You have to make sure the dependency graph works.
Instead of 10 and 9, is there a default that just runs it on all the available units?
Well, that would segfault the card. Because I've only given it 90 elements to work with.
Right.
Because each one's accessing a particular point in memory.
So you always have to pass in those arguments then?
Well, that's the difficulty, is because your kernel doesn't necessarily represent a one-to-one mapping of indexes to, your IDs to indexes is not necessarily a straightforward mapping.
Mm-hmm.
So I'll get to cases where we can be a little bit nicer later on. But in general, at every single point, you have to specify everything because you can do anything. It's sort of it's the blessing and a curse, right?
Mm-hmm.
So now the moment of truth. Let's see. You know what? I'm going to compile it. Let's just see what happens with dub build. Tension, tension. It did work before. Slightly weird. It appears to have built one thing 3 times whilst doing that. Not sure what's going on with dub there. It's probably me. Okay, we built that. Let's do L2 test. Hooray, it spit out some data. It didn't segfault, at least. I'm not going to guarantee that that's, oh my goodness, that is not good. What is going on there? It may have broken the terminal. Actually, that's not good evidence, because that's the GPU going wrong. No, this laptop does that anyway. It's fine. So actually, whilst we're here, I'm going to drop down to have a look at list devices, which was the little program we were looking at before, which takes in you ask for a device, and then you query the names of them. And I'm just going to run it with Apple as a command, because that's the name of the runtime here. So I get, it runs, come on. Hooray, you can just see that line there. Iris, Intel Iris, built-in GPU. So that's just showing that it does actually work. I haven't just made it all up. Okay, so I think back to slides now. So, yeah, a few notes. The OpenCL API is really quite large. They do deprecate things, but it's a slow process. And not only is the API large, a lot of the API is quite horribly overloaded. So things like the same function queries the size of something as well as getting the values. So it's really not, I mean, we could wrap the whole thing. Like I wrap the low-level interface, just the type-safe version, I wrap everything. A lot of that's auto-generated code. But at the higher level, you don't necessarily need to wrap everything, nor do you necessarily want to. Because, yeah, as I said before, lack of assumptions gives you lots of choices, but it also makes it a nightmare to use because it's so unclear what is the correct choice at any given time unless you really understand how it works. Doesn't aim or need to be a comprehensive D-like wrapper of every possible use case. Now, I would like it to be a comprehensive tool for every possible use case, every reasonable use case of, say, a GPU for general purpose work within the constraints of what OpenCL can do. But what I don't mean is that it should provide a perfectly beautiful wrapper for every single weird OpenCL call that you might want. Because the StatC API is there, and when you need something super weird, it's not that horrible. You can do it. But part of what I want to do is to really improve the out-of-the-box experience for using the GPU, because that, I think, puts off a huge amount of people from actually doing. A lot of people have tasks that using the GPU would be really perfect for, and they never do it just because that barrier to entry feels like too much. And so the common use cases should be streamlined and easy, but the complicated ones, sometimes it's perfectly okay to make someone call a horrible API to do something horrible. So yeah, as I say, you can always drop down. And what's really important is that I don't hold state from the OpenCL runtime, which means that at any given point, you can drop down and call the C API, and you haven't invalidated a whole bunch of assumptions that your higher level wrapping code has made. So it's been one of the things that's made the design process very hard and taken a long time is all of the things where you go, oh, it'd be so convenient just to cache that value, and then I could have this neat API. I don't really see that as a viable approach because I think it's not really the D way a lot of the time. The D way is always that when necessary, you can drop down and do a little bit lower level where necessary, and then you don't worry about that leaking out to the rest of your code and infecting everything and breaking everything, as long as you did that little bit right. So now let's move on. One nice thing I should mention is errors. Similar to people who've used the C++ API for OpenCL will know that you get some reasonably pretty printed errors sometimes. Well, you actually get to know what the error was, which is a bonus, as opposed to having to make sure that you check for the error. And then basically the solution, if you're using the standard, is look it up. It gives you a number. So I have it such that when errors happen at any point in the API, it throws an exception, and the exception has a message that tells you what the error was. It's very basic. It doesn't tell you how to fix it. It doesn't give you any hugely great information. But it's all just in a massive, great big table that it looks up, having got the value. And it's things like that where you're going to do things wrong. You're going to crash things. You're going to make a mess of things. And if it doesn't tell you what you did wrong, you're just going to give up. So now on to what Attila was asking me about. Sometimes you really just want to do element-wise, or something that roughly is a bit like element-wise. Maybe you read from a few things around yourself, but you only write to one element. So there's a one-to-one mapping between these work items and the actual data that you want to work on. So we could do what you can currently do almost. Like now we're getting into code that has been very experimental, and I've changed quite a lot recently, and it goes in and out of a state of being broken to working. So don't expect to be able to use this straight away unless you're prepared to probably hold your own copy of it and fix a lot of bugs. But I thought I'd show it to you because this is part of the goal. So we've defined a kernel just like before. All very simple, creating a buffer. Interesting here, .sliced. So that's mer or std.experimental.nd slice. So you've taken your input, you've created a slice out of it. So you've turned it into a multi-dimensional array. And it turns out that, I'm not sure it's in std.experimental yet, but in mer, given a certain set of assumptions, you can actually get the pointer out from one of these things. You've built this big multi-dimensional thing. You can get the pointer to the first element, and you can get all of the strides and all of the shape, and from that you can work out what a one. So in those circumstances, you can safely extract a one-dimensional buffer that is the underlying memory and all of the necessary strides in order to only look at the bits that are relevant. And you just call toBuffer. and it maps that and returns something that isn't, OpenCL doesn't know what shape it is. Oh no, that was a mistake. OpenCL doesn't know what shape it is, but the D side remembers, which is where I'm slightly breaking my own rules, but I think at some point you have to hold a little bit more information because OpenCL is really lacking in metadata. So then you just create a buffer, and that creates a buffer on the GPU. And then the magic line, input buff.cl map your kernel with the other argument that you wanted to the kernel, the B, and then enqueue it. So that's the magic step, really. That's the point where you no longer have to think about what's a work item or any of that. You just go, I've got a function that operates on one element, and I've got a big chunk of data. Please, GPU, go do that. And then we can just read it back. And I'm trying to make sure that things pipeline reasonably well. So when you go input buffer.read and you give it an output buffer, that returns the output buffer so you can chain it. So that's where we're almost at. That's almost ready for consumption. And that's a lot nicer, I reckon. So why not OpenCL 2.x? Why, I'm using OpenCL 1.2 for everything here, and that limits me a lot. So that CL map you saw before will have some bad performance characteristics, and you have to be very careful about the size of things for reasons that you shouldn't have to care about most of the time, to do with splitting things up into work groups and how those work groups map onto the hardware. So in OpenCL 2.x, you can have non-uniform work groups, so you can have, it's all evenly chunked up except for the edge ones that are a bit smaller, which is fantastic. But that's only in OpenCL 2, and NVIDIA, oh. NVIDIA really dragging their heels on OpenCL because obviously they've got their proprietary CUDA. So they only support 1.2. Who knows how long it will take them to get to 2.0. The hope was that they'd leapfrog straight to 2.0 and skip 1.2. They were on 1.1 for, what, 5 years, 6 years, while everyone else was on like 2.1. So for true cross-platform, you're kind of stuck with 1.2. Also, a lot of embedded devices, as the more advanced features of the higher OpenCL APIs aren't available on embedded devices anyway, because the standard allows you sort of, you can have like a bunch of get-out-of-free cards, basically. If you're writing on a small device, you don't have to implement everything. So yeah, DlangScience, which is where I'm getting my bindings from originally.
So you got about 5 minutes left, John.
Sure, yep. DlangScience only supports 1.2. Now, that's great. It's great that it existed. That kickstarted things for me. I actually generate my type check bindings from, I parse the source code and generate the bindings at the moment using libdparse, which is, okay, it's not very sustainable, but it was just a bootstrap because I couldn't be bothered to write it myself. I could probably delete the auto-generated tool and just check in the result. I should probably do that. But for now, I'm bound to whatever DlangScience supports, so that's on my list to get that up going a bit further. I'll probably have to support it anyway, even though NVIDIA aren't there, because the opportunities are just too good. It's so much easier to make a clean API. There's just a few critical things that OpenCL 2 enables that mean that you can do a really clean API with map and filter that 1.2 really struggles with. What's next? Massive cleanup is what I need to do. The level 1 is pretty much completely stable. The level 2, that is the sort of D-like API, is reasonably stable. Once you're up to level 3, it's a memory dump. It's a dump of my brain. There's stuff everywhere. So it needs a huge cleanup to be, for that layer to be really useful. Testing. Now, this is actually quite difficult because there's so many different devices. I mean, there's no such thing as a comprehensive test suite for anything that runs on something like, some GPU code. You can't have a comprehensive test suite. It's impossible because every single device will be different. And also, you're in an ecosystem that is so varied that there will be implementation bugs. And this is just a fact of life that you have to put up with. Anyone who's done game stuff will know that drivers have bugs. And that's just as true here, only there's less testing being done because you don't have the whole of the games industry behind having worked with the drivers. Although on the plus side, you don't have driver manufacturers deliberately supporting the bugs, which is nice. I really want to get information from people who use GPUs or specifically OpenCL about what they really hate, what gets in their way, what really ruins their day, because that will help me target my decisions with what things to wrap at the high level, what things to not care about. And the final goals, make D the obvious choice for cross-platform GPU control. There currently isn't an obvious choice, except for C++ and CUDA, but I don't see that as a good one because it's not cross-platform and it's tied to one vendor. And the really big goal is make general-purpose GPU usage a normal thing to do. Make it so in your program you occasionally, just occasionally, it's not the whole point of it, occasionally you have to do a big calculation on a really big array, and I want to make it such that your first thought is, I guess if I found they had OpenCL installed on their system, I'd just do it on that. And that would be, I would be a very happy person if people started doing that, because there's a lot of wasted hardware potential there. Little bonus slide. So this is where the top one is the absolute limit that I think we can get to without compiler support. And where you just take an input, you've created the buffer before, but that could be done automatically for you as well. You map a little string lambda with magic variable names, extra arguments, read the output, write it. If we had compiler support, if we had probably via LLVM, we could do that. And that would be D code, incredibly stripped back D code, pretty much no D runtime, definitely no Phobos. But it turns out the OpenCL library provides all the math stuff you need anyway. And wouldn't that be fantastic?
John,
Yep.
is this current code or projected code?
The top one, that's projected code. I haven't got that one yet. That's the, so the previous stuff I've shown is like, it's either solid or just on the cusp of being what you might want to use. This is not there yet. There's nothing stopping me. It's just I haven't got around to it. There's nothing technical that I need to work out. I just need to do it. Thank you very much.
Okay, so I have a question about the slide where you had the ND-slice integration.
Yep, let's go back to that. I have to find where it is. I think it was this one.
So
Yeah, there we go.
Yeah. So I thought, couldn't you avoid the explicit conversion to array there? Just make the interface just do it lazily?
Right. So that's it's sort of a matter of taste, that one. So the reason, so the way that the API works and the way that anything is actually going to work when you're communicating to a device, I guess it wouldn't have to, but the way it does work is that you have to have a buffer of memory that you read from. So to me, it feels like a lot of the time that copy is probably something that someone wants to control. I could make it automatic. I'm not sure. But it's one of the sort of low-level details that keeps leaking out that I really don't want to get rid of is, well, I'd love to get rid of, but I can't really see a good heuristic for it, is the cl.mem copy host pointer. So there's also cl.mem use host pointer and a bunch of others. So you are actually explicitly saying, here's my chunk of memory, copy it. There is a trick, and what I really do want to explore is the idea of generators or range-like things on the GPU. So you could, if I just go forward to this, in this case, you could compose snippets of the string lambdas, right? So you could have built-in snippets that were some sort of generator. So it would read its ID, and based on its ID, it would generate something. So something like IOTA obviously is trivial, because that's probably just going to be your ID. The other thing that's worth noting about the ND slice integration is striding. That's just something I was trying to get done for the conference, but didn't quite get there. So you do actually have to be, at the last level, you have to be contiguous. You can't, it doesn't automatically handle skipping. You can still manually do it, but it doesn't work it out all for you.
Could maybe CLMap allocate the output buffer for us instead of having to do it and then do .read?
Oh, that's actually a bug in that code. That's wrong, because there is no output buffer. If you look at the code, I write back into the input buffer.
Well, when there is, though.
When there is, I have considered this to implicitly create output buffers. I think it's a possibility. Generally speaking, in that case, where you actually want to have an input buffer and an output buffer and map that, you're probably going to want to write quite a lot more code in the kernel for certain anyway. Because if you're going to chain a bunch of operations, you don't want to read from memory, then write to memory, then do the next one, read it all back again, and then write it all. Really, you need to compose little snippets that locally output just to a register. So, yes, kind of, maybe.
All right.
There's a couple at the back.
So I was wondering about the asynchronous API. Is this an issue of implementing it once and dropping it away nicely under a nice layer of I don't know, future or whatever interfaces? Or is it going to be a continuous waste of or continuous requirement of effort to keep it actually bug-free?
So I didn't catch the very beginning.
So the asynchronous stuff where you mentioned the interface is hard to use, can we rob this away once or?
Yes. As a matter of fact, I kind of have in a thing that I haven't talked about in this. I have I talked a little bit about it last year as an idea where you treat the dependency graph of kernel executions as sort of the fundamental thing. You consider OpenCL to be a scheduler and look at everything from that perspective. So you create tasks and then go, you depend on A, B, C, and D, and then you build up a dependency graph and then just give it a kick, and it goes and does it all.
Thanks.
Yeah, I think again there's another.
You're going to be a bit louder, please, sorry?
I think again there's another great opportunity for CTV if we just would dial up the domain-specific language approach and would do our own domain-specific compiler at CTV that would be able to chain those things, and that is certainly doable. It's relatively easy to analyze as far as I can see, so that would be great if we would do that.
Yes. The only difficulty is that if you use quite a strict subset of the language, you're fine. There is a little bit of a difficulty because the OpenCL C is still C and has the preprocessor and all of that. So, you know, it's not all sunshine and rainbows.
We got time for one more.
How does fit the SPEAR intermediate representation into the AP?
So you say, how does SPIR?
Yes, how it is used in this API.
Oh, so in the current system, I'm not using it at all. I'm compiling straight from the C to the implementation defined something that eventually gets run. So conceptually, this one, I would imagine that would go to SPIR. I mean, I could compile it to SPIR now. OpenCL 1.2 supports compiling OpenCL C to SPIR. I could do it. I just haven't seen the. It's not something that matters to me, and it didn't seem a priority. Although I do recognize that for some applications, it's really critical because you can't share your source code.
Okay, thanks.